Okay, this is Math 1151. It's Friday. Only, 4 more weeks left? Oh, geez. How are we going to do that? Okay, well, anyhow. Today we're going to cover 4.6 from our textbook. And I'm going to do it by asking 3 totally unrelated questions. Let's see. Okay, question 1. Suppose, this says suppose you toss a ball into the air and catch it on the way down. Was it moving at a speed of 0 at some point? Was the velocity? Yes. Was the velocity done 0 at some point? So as a visual aid, we have a ball, and I toss it up. And of course, that's not on the camera, so it'd be really cool if I could just toss it up and never come down. Right? It'd be, yeah. Well, it's gone now. Yeah, the other day in class, I lost my lecture notes literally 5 minutes into class. 5 minutes, it was like, poof, they're gone. And I was like, I guess I'm just going to make the rest of it up. Okay, so let's, here's my first question. Okay, so I'm going to ask 3 questions, and I'll ask them kind of in turn. My first question is this. And I hear people telling me, yes, the ball's velocity was 0, and here I'll toss it up again. Its velocity right there. Right there. 0. Okay. So we have a theorem about this in mathematics, which you may now think is obvious. I don't know. And it's called Theorem. Here it comes. It's called Rolle's theorem, I guess. I want to call it Rolle's, but I don't know. There's my ignorance for you. Okay, Rolle's theorem. Okay, so suppose f of x is differentiable. That means you can take its derivative. That's all that means. You can take its derivative, okay, on the open interval AB. Okay. It's continuous on, I probably don't need to be so precise, but whatever, on the closed interval AB, and f of A equals f of B. Okay, so what's this saying? So in real life, here's what's happening. The interval is time in real life, and time starts now. So here's A, and then here's the ball. It's at this height at time A. I'm going to toss it up in the air. And at this point, this is B, time B right now. We're back where we started, right? So if you go someplace and come back, then it says, Rolle's theorem says that f prime of C is equal to 0 for some A less than C less than B. So there's some time in between when the derivative was 0. Okay, yeah, so the question is, isn't that kind of like the intermediate value theorem? And there's a lot of value in calculus, right? You have all there's all these value theorems, right? There's the intermediate value theorem. That says, what do you use the intermediate value theorem for? To find a root, typically. To find a root. To find a place where your function's 0 or equal to another. Then you subtract and you make one side 0. That's what the intermediate value theorem. It says that there's an intermediate value, right? Another value theorem is the extreme value theorem. It says that if you have a closed interval, then your function reaches a highest and lowest point on that closed interval. And this is something about, there's some value. So it's kind of like the intermediate. It's saying there's a value where the derivative is 0. And so if we were going to plot the balls, if this is time here, here's time A and B, what we're saying is when we toss it, here they are at the same value. That's when you caught it, right? There was some point where the velocity, and the velocity corresponds to the first derivative. That's perfect. Where the velocity, oh, look at my tangent line. This is the worst horizontal tangent line ever drawn in a calculus course. There we go. Here's my, there we go. Looks better. So it says that the slope of the tangent line is 0 at some point. So I think, you could say, well, this question's obvious, but, Rolle's theorem here, I think, completely addresses it. If you reinterpret the question, do you understand what I'm saying? The ball had to have velocity 0 someplace. All right, so this is like a very physical idea. All right. Let's do, I could prove these, but I don't think you want to see it, so let's not. Okay, that sounds good. Okay, so we'll just like work problems and then go home. That's my philosophy. If I can figure out how to work those problems, I wrote them. Okay, so now, question B, unrelated question B. Ooh, okay, suppose you drive a car, like you're going to drive something else, okay, on a toll road, from one booth to the next. From one booth to the next. Okay, good. And this is this distance. This distance is 30 miles, and it takes you half an hour. It takes you half hour to drive 30 miles. I could have shortened this problem down. I'm sorry. Put so much context in it with the toll booth. I could have added some change. Stop by, got coffee, whatever. Here's the question. Must you have been driving 60 miles per hour at some point? Must you have been driving 60 miles per hour at some point? Well, what's the answer to that? Can you guys tell me the answer to this? Yes, why? He says if you don't do, I'm going to give you a hard time, I'm sorry. He says if you don't go consistently 60 miles per hour the entire way, you're not going to make it in a half hour. Let me ask you this. Did you drive consistently 60 miles per hour? No, why not? You start off slow, right? And for all the times that you're going slow, you must be going faster than 60. What's up? She says 60 miles per hour is the minimum amount of speed. What's that mean, minimum amount of speed? I think what she means is if you were going to drive the same speed the entire time, then it's the minimum that you'd have to go, right? If you're going to drive the same speed the entire time, then 60 is actually the exact speed you'd have to go, right? All right. So this corresponds to what's called the mean value theorem. The mean value. This is our next value theorem. The mean value theorem. So suppose f of x has a derivative on the open interval AB and is continuous on the closed interval AB. Then f prime of c is equal to f of b minus f of a all over b minus a for a less than c less than b. Why is it called the mean value theorem? Is it because it makes you angry? Yes? Well, why is it called the mean value theorem? It's like an average here. This is like an average. When you find the mean, you find the average. And here, we're kind of taking the top. Now, what's the connection? Here's a good question. What's the connection between the mean, the average value theorem, and Rolle's theorem here? Okay, that's a good point. So he says, well, it looks like suppose f of x is differentiable. Suppose f of x has the derivative. Those are saying the same thing on this open interval AB, on this open interval AB, and is continuous on this closed interval AB. Oh yeah, it's the same setup, right? The same setup. And then the punchline's a little different. This one says f prime of c equals 0, and this one says f prime of c equals this average value, right? What's the connection though? Slope. What else does Rolle or Rolle's theorem say? F of a equals f of b, right? And what's that mean over here? It means the numerator is 0, right? This is a special case of the mean value theorem. This is the case when f of b equals f of a. Does that make sense? And so what we're trying to do is we're just trying to give you guys some intuition on these are not really abstract things. All of you seem to know that when I toss up the ball and catch it, it had 0 velocity at some point. Well, this is the exact same idea as if I'm going to drive 30 miles and it takes me a half hour, then I have to have been driving 60 miles per hour at some point. They're very much related ideas, even though the context seems different. I mean, that's really the whole idea of mathematics. People complain mathematics is abstract, but that's the good thing. You can see different situations as being the exact same situations. And instead of having many, many different solutions, you just have one solution. That's the cool thing about calculus. The dirty secret about calculus is that before it was invented, we could solve all the problems in a calculus book. We didn't really gain much by inventing calculus, except for the way we solved all the problems was totally different each time. It was like, oh, that new problem? Here, I'll work really hard. Oh, that new problem, I'll work really hard to solve that one. Oh, that new problem, I'll work very hard to solve that one. With calculus, we're able to see these problems are all the same. Maximizing a function, how do you do it? You take a derivative, right? I want to know how fast a function's growing. I take a derivative. I want to know something about intermediate stuff. Well, look, I'm going to do something with a derivative here. Derivatives, derivatives, derivatives. Oh, yeah, and I can draw a picture for the mean value theorem, too. Let's do that. So picture time for the mean value theorem. I'll draw a very pretty picture. Here it is. Here's x. Here's y. Here's my function. Looks nice and smooth. Here's a. Here's b. And the mean value theorem says, hey, what you do is you connect a and b. Look, what's the formula? What is slope again? How do you compute slope? rise over run. This is rise over run, right? y2 minus y1 over x2 minus x1. Well, here it is. So you have this line here. You have this purple line. And the mean value theorem says that there's some point on our curve. I'm guessing it's right here. Oh, I didn't really hit the curve. OK. Let me try one more time on that one. OK, Bart. Pressure's on. There we go. There, that looks a little better. There's some point, and this corresponds to C, where the slope of the tangent line is the same as that other slope. Make sense? There could be tons of points. There could be many, 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 many points. Probably only a finite number, probably. But yes, there could be lots of them. I'm not sure about the infinite number one, but it's not too crucial. OK. So now, we just answered 2 questions. Oh, I have a third question. Let's see what the third question. Oh, here it comes. OK. Suppose 2 functions. OK, so now here's where we're getting kind of abstract on you. Suppose 2 functions have the same derivative. Suppose 2 functions have the same derivative. What can you say about them? Now look, this is kind of funny because this is a very different question. The first question was about tossing a ball. The second question was about driving a car. Now this is about 2 functions having the same derivative. Right? Yeah? Maybe same change but different position. And so can you give me, so answer, here's an answer, answer 1. Same change. So maybe same rate of change, but different positions. Okay, so like an example of that would be, if I toss the ball like this, or if I sit down and toss the ball up here, if I toss it the same height, at the same initial velocity, its rate of change is the same both times, right? But its overall position was different. And so, yeah, I think those 2 functions should have the same derivative, right? So let's see if we can do something let's see if we can make this a little bit more mathematical. This might not sound like math when I'm tossing balls and sitting down on the ground, but we'll see what happens. Okay, so try to make this a little bit more mathematical. There we go. All right, so here's a fact. And we'll explain why it's true. So first I'll state the fact, then I'll explain why it's true. Fact, if f prime of x equals 0 for all x in some interval, I, yeah, that's the name of my interval, okay, then f of x is constant on I. Okay, all right. So that should make sense. You guys believe that? I would believe that. I think that makes sense. Now let's use the mean value theorem really tells us this, okay? So, what's the mean value say? What the MVT? So we have the IVT, the EVT, the MVT, right? What's the MVT, mean value theorem, say about this? Question mark? Well, don't erase the mean value theorem, Bart. Let's see. Oh, no. Yeah. So we have suppose, this says suppose A is less than B. Okay, well, whatever. A is less than B. By the MVT, what do we have? Well, we have that f of b minus f of a over b minus a is equal to f prime of c for all c in between these, right? And what do you know about f prime of c for all c on that interval? It's 0. It says it right here. Oh, wait. Yeah, there. That's where it says it, right there. Equals 0. Okay, fine. Since b is greater than a, b minus a, not 0, right? Not 0. So I can multiply both sides by b minus a, and it gets sucked into the 0 and goes away. And now we have f of b minus f of a is equal to 0. And so then f of b equals f of a. And that's what we wanted to say, right? We wanted to say that our function was constant on the interval. Sounds good. So this is a little application of the mean value theorem. That's all this is, okay? So our function, that says function, is constant. On I. Now we still have this is our third question here, and we still haven't answered it yet completely. Although, I think this is a very compelling answer, but it doesn't really feel like calculus class yet. Haven't been talking about derivatives or anything. Eraser. So, we know this. Don't erase the mean value theorem, Bart. You can erase this. Okay. So we're going to try to answer this question right here. That's what we're going to talk about. Two functions have the same derivative. So we're going to do a trick. Two functions. F and g have the same derivative. Here's our trick. You set h prime of x equal to f prime of x minus g prime of x. These two functions have the same derivative on our interval, right? So what's it when you subtract? What do you get when you subtract them? 0. So now h prime of x is equal to 0. What's that tell you about h of x? H of x is some constant. So by this fact over here, so by our fact, h of x equals k for constant. Okay? So what's that mean? If h of x equals k for constant. Yeah, it's fine. What's that mean? It means that, I probably should have said this first. I'm sorry. Set h of x equal to f of x minus g of x. I'm sorry, guys. I should have said this first. So this equals this. This still equals this, right? That's OK. Aha. And so now k is equal to f of x minus g of x. And so k plus g of x equals f of x. OK, well, I have a lot of functions. I've said f of x a bunch of times. I have some pluses and some minuses and some letters and everything. But what is this really saying when I have these things? They differ by a constant. They differ by a constant. It means exactly what our first answer, same rate of change, right? But the position is slightly different. It's higher or lower. And so we start to draw pictures like this. If we say, let's see if I can draw this picture. So I have some function here. There's a nice function. These functions, if I draw them correctly, will all have the same, don't use blue again, Bart, will all have the same derivative, but just be differing by a constant. Right? There we go. Have some fun. I know you get the idea, but I have one more color left, so I have to take care of it. There we go. So here we have, I have a bunch of functions there. It looks like 6 functions. And if you can use your imaginations just a little bit, you can imagine that all these have the same derivative, right? But they're just shifted up or down by a constant. That's what's going on. The derivatives can't tell the difference between, when you take the derivatives of all these functions, you get the same curve each time. The functions are all increasing at this point at the same rate. They're all 0 somewhere near where I'm touching right now. And they're all decreasing after that at the same rate. All right? So here's an example of something that we do. Oh, should I be? Yeah, why not? Okay, so, all right. F of x is equal to sine of x. F of x is equal to sine of x. Give me all functions that are equal to this one. Sorry, that have the same derivative as f of x. What do? What's a function whose derivative is sine of x? Negative cosine. That answer is almost too good, you know. Cosine is correct. It's absolutely 100% correct, right? Because the derivative, so if I say capital F of x equals negative cosine of x, we just take the derivative. The derivative of cosine is negative sine. The negative sign hangs a different sign. Well, okay. Yeah, so the derivative of capital F equals the derivative of lowercase f. Can you give me another function whose derivative equals sine of x? Any constant. So we could say or equals negative cosine of x plus 6 equals or equals negative cosine x minus 2. And usually we just write something like plus k, and we know that k is a constant, that sort of thing. By the way, these equal signs here, I'm not saying these ors are kind of separating them. You with me here? Okay. That question was pretty easy. Wasn't too bad. I'm going to ask a harder question, and it scares me, but I'm going to do it anyway. I'm a little afraid. So here's my harder question that I'm going to ask you. Now, okay, so I want to know whose function I say f of x is equal to 1 over x. Whose derivative is f of x? And I'm going to say x is positive. X is greater than 0. Yeah, whose WHOSE derivative is f of x? Question mark. Answer that people said to me, natural log of x. And is there more than one answer? Okay, give me what? Plus a constant. Natural log of x plus k for a real number constant. Very good. All right. So now let's do another example, okay? Are you ready for this? Okay, so f of x, g of x equals 1 over absolute value of x when x is less than 0. Can you tell me this? What's the answer here? Natural log. He says natural log of the square root of x squared. And how do we check his answer? Square root of x squared. How do we check his answer? We just take the derivative, right? That's what you're saying, right? We just take the derivative. Okay, so yeah, let's check this answer and see if it's right. Sounds good to me. Okay, so we write d over dx of natural log of square root of x squared, right? And, what's the derivative of natural log? It's 1 over x. So it's going to be 1 over the square root of x squared. Oh, my God. And then times what? Okay, so I'm hearing lots of confusing things to me. Times, okay, so it's going to be 1/2, right? Because I'm bringing down I'm taking the derivative of the inside. This is x to the 1/2. You guys with me here? And then that's going to be 1/2 times x squared to the minus 1/2, all times what? 2x, right? So this is the full answer. Now let's simplify this just a little bit, and I'm going to have The 2's are going to cancel, right? And then what's going to happen? Let's see. What are we going to get here? Do the exponents cancel? Well, something's going to happen. Let's go ahead and write it again. So it's going to be 1 over the square root of x squared times 1 over the square root of x squared, right, times x, right? Now what happens? The radicals will cancel, right? Is that right? 1 over x squared times x equals 1 over x. Is that okay? What do you guys think? I thought I wanted 1 over absolute value of x. Why? Oh. She says it's been squared and canceled when I take this derivative. What about when x is negative, what's going to happen here? This is going to be positive here? Why? I'm sorry, I'm being stupid, but just help me out. Mm-hmm. Are you saying here? 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 Oh, what do you get? What is that right? It's going to be positive. We're going to have 2 x's. We're going to have minus. She's saying this. She's saying you have x over x times x like this. And when I plug in negative 3 to this, you're saying I get positive 1/3? I'm just asking. What's going on here? The original function right here. Oh, in the original function, he says, okay, well, maybe, okay, yeah. He says, in the original function, this will be the absolute value. It's going to be positive. So this is going to be, okay. And what is this right here? What's another way of writing this? Absolute value of x, right? And how do you get different answers here? Yeah. But, okay, so I said g, and I said whose derivative is g? And you say natural log of absolute value of x plus a constant. What letter should I use? Okay, so plus L. I ignored everybody's advice to write down k. Because when x is positive, isn't this equal to this right here? Right? And what does, I guess what I'm saying is, the derivative of natural log of x is, what's it look like? And we want to know whose function is the derivative natural log. What's natural log of the absolute value of x look like? There's natural log of x. What's natural log of the absolute value of x look like? He says the same thing on the other side. What if I raised it up like, oops. What if I raised it up like that? Does that change the derivative? Do you understand what I'm saying here? This is a little sticky situation. I should say that more often. So here's natural log of x. Here's natural log of x when x is greater than 0. And this is natural log of, this is going to be natural log of absolute value of x plus plus L plus a constant, right? When I take these derivatives, don't I get 1 over absolute value of x both times? I'm just pointing out that the constants here, because you have this kind of discontinuity in 1 over x, right? The constants can be different. This is a little bit of a hairy issue that should maybe come up right now, because we're talking about functions and what could they be. All right, is that okay? All right, so let's do some problems, and then it can be done. Okay, so standard mean value theorem question. Here it comes. F of x equals x squared. Find c in -1, 2. This means c that's in the interval. It's a little, you make like this sort of shape here, and then you put a line like that. That's how you do it. Okay, so find c in the interval so that f prime of c equals the slope between the endpoints, whatever that means. Mean value theorem, that's what we're doing basically. All right. Yeah, what's that? What's going on? She says, what's going on right there? Yeah, I'll explain this. I'll do it really big. Okay, so we have c is a number, right? And -1, 2 is the interval, right? Between -1 and 2, not counting -1, not counting 2, right? And then this symbol here, like so, means that this is just, it means -1 less than c less than 2. This right here, this is called element of. Element of. Good? Who asked that question? Okay. All right. So how do we do this? We use the mean value theorem. Well, we don't even have to use the mean value theorem. We just basically do what the mean value theorem says. So f of, we're doing x squared. So what's f of 2 equal to? 4, right? What's f of -1? 1, so it's 4 minus 1 over 2 minus -1, right? We want f prime of c to equal this, and so we get 3 over 3. So we want f prime of c to equal 1. Okay, and so well, that just says that 2x is equal to 1. Can you guys find such an x? Yeah, x is equal to 1/2. All right. Yep. Oh man. Okay, let's do number 5. This is from the Mooculus stuff. This one's one of my favorite questions. Okay, so so f of x is equal to x minus 3 squared. Well, to the -2. X minus 3, sorry. To the -2. Okay. Is their value c in 1, 4 such that f of 4 minus f of 1 all over 4 minus 1 equals f prime of c. Now, this sounds a lot like the mean value theorem, right? Is it the mean? Does this follow from the mean value theorem? I see some people shaking their head no. Why not? Is my poker face not good enough? My poker face looks like this. Yeah, so what's the deal? Why doesn't this follow from the mean value theorem? What's the problem? What? Is the function continuous on the interval? What's the function look like? It looks like it's 1 over x minus 3 squared, right? One over x minus 3 squared, right? And so what happens when x equals 3? It's not continuous. It's going to be, I mean, we are now very savvy people, and we know the function's going to look like something like that, isn't it? Yeah. And so what's going to happen is, if we try to solve this, we're going to say, well, let's see. F of 4, we're going to be able to figure it out. We're going to be able to show there is no such point. All right? And does it contradict the mean value theorem? No, it's not continuous. Mean value theorem does not apply at this point. All right? Hopefully we don't ask you any trick questions like this. All right. Let me now ask you my favorite question, and hopefully I don't screw it up. But we'll see what happens. As I'm talking to you right now, I have no idea how to do this problem. So we'll see if I can figure it out after I write it down. F of x is differentiable on all real numbers. F of x is differentiable on all real numbers. F prime of x is not equal to 0 for all x. So f prime is never 0. F prime's never 0. Must f have a root? What's the answer? Okay. What's the answer? How are we going to try to solve the problem? What? We could try to take it. Well, we can't really, he says take a derivative. That's a good idea, right? A derivative is kind of taken for us. This is never 0. Must f have a root? Okay? Maybe what we should do is we should say, what would happen if we should try to use the mean value theorem somehow to help us out. We should try to use the mean value theorem. But how? What do we write? Must f have a root? She says, I don't see any reason why it should have to have a root. Can you give me an example of a function that doesn't have a root, where f prime of x is never 0? No, time's up.